Okay, 6 o'clock. Let's get started. Good evening, everyone. Let me just turn on the recording first. Where's the recording? Okay, so this time we will be focusing on somewhat called a logic design, and let me give you a quick introduction what we are trying to do at the overall scenario. Before I start, is there any question from anyone of you? Okay, no, seems like there is no question. So let me share the Jamboard with you. Okay, so it is possible at the electronics level that we construct logic operation. We call it a logic gate. We'll call it a logic gate. Sorry, what has happened? We call it a logic gates. So basically, uh, what are these? These logic gates are your just hold on. Let me see. There is a problem going on in my system. Let's just start. This will work. Okay. So these are electronic component. These are electronic components on piece of silicon as a material. We won't go detail into that, but I think you are all familiar with the microchip concept, and if you have chance to open up any computer board or anything, you will see there are microchips like these. You can see on the visible side, or they can be other configuration as well. A plastic body, and then some metallic pin is coming out, and they're on the motherboard, and so on and so forth. But what is inside here is a piece of silicon, very small piece of silicon, okay, like maybe 1 millimeter by 1 millimeter. And in that area, there are like maybe millions of gates, millions of logic gates. These contents, okay. Now these logic gates are the fundamental uh, like concept that we want to pick up in this class. In the next classes, like not next classes, I mean next course, CS147, we'll also have a little bit sneak peek on how these logic gates are built up. But that's not important. Important concept is that we can build logic function like NAND, which is like say A, B, not. So this is a logic function. And that electronic component, we draw a picture. This is a symbol for that electronic component called NAND. And then there is this electronic component like NOR, which does nothing but A or B invert. So that symbol is this. and there is an inverter gate, which is basically a bar symbol like that. So, and of course, by combining NAND with a NOT, let's say we drive one with another, we basically, what we get is a equivalent of AND operation. And then if we combine NOR with OR, we build a OR logical operation. However, the fundamentally, so these are the fundamental logic gates which you can build at the silicon with a physical uh, this physical area. We can build them, and what they serve as a purpose is that, saying that, let's say this is my NAND, or I should not draw like that symbol. Let's say I built up an electronic component. How it is built up is kind of a black box right now. And there are two logical input, A and B. And there is an output out of that. Okay. So what all we are saying, if we are setting input A and B logic to 0, 0, we'll observe a logical value at the Y output as 0. And then let's say if it is 0, 1, then we'll observe a logical output at Y at 0. If it is 1, 0, then we'll observe 0. And if both of them are logical 1, we'll observe 1 here. So this is practically what we are talking about AND gate inside that as a logical component. Okay. And now the question becomes how we are going to set up these logic values or probe and find out, okay, this is the logic we are getting at the output, is basically it's done by setting up electrical voltages. Okay, so let's say this whole circuit or this whole chip is operating at 1.5 volt, that operating voltage. Then if this guy is 1.5 volt, electrically we are setting into this pin, and this is like a 0 volt, electrically setting into this pin, we'll observe a 0 volt at this point. Now if we change this 0 volt to 1.5 volt, we'll observe a 1.5 volt here. So this is my logical high, this is my logical high, this is my logical high. So electrically, logic high, logic low, it means this presence of voltage, absence of voltage, very crude sense you can take like that. But in this class, we'll be actually living in the logical domain. We'll always refer this operation as a logic value setting. We don't get into the electrical area at all. Question so far? Okay, now saying that we can build a logic gates like that, that means given a problem, given any problem, mathematical or otherwise, or logical, if we can express the solution in terms of Boolean expression, we should be able to build corresponding electronic circuit. Okay, so our target is that given a problem, whether it is a mathematical in nature or logical in nature, if we can express the solution as a terms of Boolean expression, we can actually develop an electronic circuit, electronic chip, electronic component that actually evaluates that logic and solve the given problem. For example, let's say we come up with something like solution, or we express a solution of a given problem, something like this: x, y bar, or z. Some arbitrary problem. Don't worry what this problem, how this solution came up. We'll discuss that in successive classes, lecture topics. But let's say we came up with this Boolean expression. Each of them is a Boolean function. Then what we can do here, we can actually build a electronic circuit using logic gates, like this, like x, y. We need to do a inversion of that, use a NOT gate, then AND them, then OR with Z, or with Z. Since each of these logic gates are electronic components, that means this pretty much is implementable on the piece of silicon as an electronic component. And this one, we basically call it a logic circuit. So this is no longer an electronic circuit we are talking of. Of course, at the end of the day, the entire thing is electronic circuit because internally they are all electronic component. But at our level, at our abstraction level, we call them a logic circuit. It is a bunch of logic gates interconnected with each other to evaluate one solution. Question? Okay, now you see this type of logic solution. What we are seeing, your output, let's say it is F, or okay, let me not do F, but let's pick up another symbol like K. K. So K is a function of X, Y, Z, where X, Y, Z are basically our primary input. And this one is called a primary output. Okay, so function, primary output, is a function purely on the primary input. Okay, and this is what called combinational logic circuit, where basically if you change any logic like 1, 0, 1, this logic evaluation always propagate forward in a forward sense and ultimately comes out to some value. We don't know. We need to see what this value is. But logic propagates in a forward direction always from input side to output side in a combinational logic case. But these modern computers are basically combination of the combinational logic circuit and also something called a sequential logic circuit. This is very much important. This is sequential logic circuit. Computers are sequential logic machine. Computers are sequential logic machines. The concept of the sequential logic circuit is like this. Like, let's say I have primary inputs X, Y, Z, and then I have the output, let's say K, okay? And I have another output. We call it a, let's say, let's mark it as QT plus 1, just as a naming, and we call it next state, okay? And that next state goes and stored into a storage element and being applied to the logic evaluation itself later on. Let's say we call it a QT, which is a present state. And your function K is X, Y, Z of QT, whereas QT plus 1 is a function, another function, maybe it's not the same function, of X, Y, Z and QT itself. So there is a temporal relation between this output and this input. This output QT plus 1 is actually evaluated based on the current input and the previously computed result. So this is somewhat is a next computed result coming in, stored, and in the next step, iteration step, those will be getting feedback into this whole circuit, and that's the sequential logic circuit component. But in this class, we won't be dealing much or at all with the sequential circuit component. We'll be dealing with this sequential circuit more in the CS147. So we don't need to be worried about much about that, apart from just to have the conception that there are sequential logic circuit, and our modern, all the computers are basically a sequential logic machine. And in very top level theoretical view, sequential machines looks like this. Question? All right, now it comes to an concept of the universal logic gates. Okay, concept of universal logic gate, that's very important. So remember, like our fundamental logic gates are NAND, NOR, NOT. Sometimes we call it an inverter, sometimes, yeah, NOT or inverter, it's just basically the same thing. If you recall, your fundamental Boolean operation are AND, or, NOT or inverter is right there. And we see that we have this, we know the symbols of each of these gates. This is NAND, this is NOR, and this is invert. This is AND symbol, this is OR symbol, and this is AND. Okay. Now we call this NAND and NOR as universal logic gate. So you see, like these functions, this fundamental Boolean operation can be constructed, we have already seen that, can be constructed using using fundamental logic gates. So we don't need anything special about that. Now let's say about the NOT. Like let's say NOT is what? NOT is A bar, right? Let's say input is A, output is Y, it is A bar. So it is nothing but, right? By identity formula, we can write it. That means now you see this function is an AND. So practically, if you do like this, A, and just make a logic 1 right there statically, okay? Your this whole configuration is actually acting as an inverter, right? And similarly, we can do other things also, like this is almost equal to A NAND AND of A. So this is basically NAND. So you can actually do this as well. This will act as an inverter. However, I prefer electrically, I prefer this one. This operation characteristics is much better with this configuration than we are tying off the same A to both the logic port. But that's from electrical perspective. Logically, they are equivalent. Okay. So we can use NAND with this. Now, let's see, how about this one? Let's say I have a function y equals A or B. Okay. Y equals A or B, I can use a De Morgan to make it is a problem of just this is using De Morgan. So that means our this guy is a NAND with the inverted form of A and B. Inverted form we already got how to get it from with a NAND. That means A or B, I can actually express something like this. A1, that gives me A bar. B1, that gives me B bar. NAND it. That's practically give you A or B logically, right? So see, now I can actually use NAND gate to construct a NOR. Okay. So that means if I have a NAND gate and want to use only NAND gate to implement any logic, given arbitrary logic expression, I should be able to do it because I can express OR with a NAND. Okay. I can, I can actually, our target was, sorry, my mistake. Our target was to make a NOR here, which is not a problem, which is basically have one more inverter out of it. So this becomes my A NOR B. Okay, so that means my extended, so enter these things is the NOR. Okay, so I can build a NOR with NAND. I can build an inverter with NAND. That means given any Boolean expression, I can translate into a NAND only expression and use NAND gate only. So that's why NAND is an universal logic gate. Similar thing we can do for your OR. Let's see. A bar is nothing but A or A whole bar or A or 0 whole bar. That means I can build something like this. That will become my inverter. Or I can do this as well. That will become my inverter. So this guy is an inverter using NOR, And how about the other one? Let's say A NAND B. Can I do that? Of course, I can do it. It's basically A bar, B bar, whole bar, right? So that means what I need to do here is do a bar, do a B bar, pass it to an OR, and invert it. So this basically become your A NAND B. So this whole structure is my A NAND B. So given a, that means given a any arbitrary Boolean expression, we can use De Morgan's to convert it into the NOR only expression and use just a NOR gate to implement that logic. So that's why this NOR and NAND are your universal logic gates. I have a question from Carter. Let's see, why would you need to express these fundamental gates in terms, of another? Let's say in your, at your hand, you don't have any other component but NAND, electronically say. Then you need to be able to build it, okay? That is one way of looking at this problem. The real thing is lies in here. Like you see that there is this concept of timing, right? Every synchronous circuit, they operate with respect to the clocks, and that means the timing sense and delays are basically very important to tightly control throughout the logic circuit at the electronic level. Now, let's say you are building up a logic circuit, which is logically sounds very good, but some of the gates like NOR gate you get from the vendor is slow. You get the faster NAND gate, okay? So you need to see if you can replace the NOR with a NAND to get a better delay, better like faster performance out of that, so that your circuit can operate electronically in sync with the clock. So this is the main issue there, to kind of fundamentally swapping things, one logic with another. Can we do that at that moment? But that's too complex for this class to pick up. So that's why, like, fundamentally you can think right now that given the library, you have a vendor who supply you with the logic gates and doesn't have a NOR gate there, which is kind of very lame, but let's pick up in that way. Carter, is that, I know that doesn't make completely sense, but in somewhat sense, I would say. What do you think? Okay, so is there any other question from any of you?
Professor, what's the
Yes.
difference between fundamental Boolean function and fundamental logic function?
So fundamental, not the fundamental logic function. We talked about the fundamental logic gates. So fundamental Boolean operation is those fundamental operation that is being defined at the Boolean algebra at the mathematics level. So that is the fundamental Boolean operation. Now, fundamental logic gates are those logic gates which can be built up on a piece of silicon, okay, as electronic circuit. And there we can build NAND, NOR, and inverter. So they are the most fundamental component at the electronic side. To build up an AND, we need to combine NAND and NOT together to build an AND electronic component. So that's why AND logic gate is not a fundamental logic gates in the electronic side, though AND is a fundamental Boolean operation.
I see. Thank you, Professor.
Okay, what else? 6:30. Maybe if we don't have anything else, any other question, I'll let you go tonight very early. And then we'll see you all in next Monday. Oh, there is a quiz coming up this weekend, I believe. It's on those last two lectures, Boolean algebra review. Please make sure you complete that quiz. It will be open up on Friday morning as usual, just like the other quizzes, and you need to submit it by the Saturday, 11:59. Okay then, good night everybody, and see you next week.